welcome back. So far we have seen we have only given intuitive proof for the Fourier integral theorem and defined what is a Fourier transform. Just to give a motivation why we have to define a Fourier transform like that, and Fourier inverse transform, Fourier integral theorem will give you Fourier inverse Fourier transform of it, okay, of the Fourier transform. So we have defined both of them. With that we though we are yet to prove rigorously what is the proof for the Fourier integral theorem for an piecewise absolutely integrable function over a full real line. That means it is a non-periodic signal. For a non-periodic signal we want to have a Fourier integral representation. So that gives you the definition of Fourier transform and inverse Fourier transform. And we have seen many examples of for finding Fourier transform and its inverse transform, right from the usual functions and also on generalized functions such as delta function. And when you apply for usual functions, when you see that Fourier transform definition is actually it is not converging definition. If it exists, it is actually you have seen that it is actually in terms of generalized functions. For example, constant function, if you find the Fourier transform, it involves delta function, or piece what is that one, step function, that is Heaviside function. You have seen that it is in terms of in terms of the generalized function delta function, okay, generalized function, that is delta function. We will look at one more example before I proceed to find the properties of the Fourier transform. This is some rapidly decreasing function such as exponential function, e power minus x square kind of function. So this is actually kind of if you actually plot this e power minus x square, it looks like a bell curve. So if you actually plot this thing, it looks like this bell curve. So asymptotically it goes to 0 and then so it has a kind of bell. So it is a e power minus x square kind of function. So if I choose such a thing, e power minus ax square, a is positive, what happens that you will see how to find the Fourier transform. So this comes actually because this is a Gaussian kernel which comes in the heat equation of heat equation. So when you try to solve the partial differential equation, heat equation with the initial boundary conditions, so in the applications of the Fourier transform, we will try to encounter this function as a kernel. So the kernel is a Gaussian kernel, that is also called Gaussian kernel, which is rapidly decreasing. So as you see, so heat equation is a diffusion equation, diffusion of a heat, so which is rapidly, so diffuses, it goes to anything, heat is dissipates very fast. So that models like this. So that is the reason you will encounter this exponential function, rapidly decreasing exponential function. So you need to find if you want to apply and try to solve that boundary value problem, you may need to find a Fourier transform of such function. So we will just try to show what is that Fourier transform of such function. So let us start with this example. So find the Fourier transform of e power minus a square x square. Let me take like this, a is positive, does not matter. So a is negative or positive, a square is always positive, so it is fine. So if you take like this, so the solution, what you see is the Fourier transform of this one, of the function fx, let us say I call this fx, so that you can write f cap of xi, that is what you want, 1 by root 2 pi minus infinity to infinity e power minus a square x square fx e power minus I xi x dx. This is what you have. So this is equal to 1 by root 2 pi. What I do is I do small trick here. What you see is you try to put it together. So you get a minus a, so you try to write something minus square, that kind of thing. So ax square, so I have ax and I have finally to get I xi x, I xi x if you want. So, what you need is I xi I xi. So, if you add something, some quantity a square, so what you get is a square x square plus a square plus 2a x. So, this quantity is actually what you want is equal to minus I xi x, so, right. So, not minus I, so this plus I xi, because minus I take it out. So, this together, so this sum should be equal to this one. So, that makes it what is a equal to x x goes I xi by 2a. Okay. So, if you want this quantity to be this, so your a should be that. So, if I choose a as I xi by 2a whole square, this whole square if I take, okay, and then what happens to, so this square is now a square x square is there, when you say take 2ab, that is this one, and what is left is e power minus I square xi square by 2a. So, this one minus minus plus, so you have e power minus minus plus, you have xi square by 2a. So, that is you already have, so you have to multiply with this minus of that. So, if you multiply with this xi square by 2a, xi square by rather 4a square, right. So, this is 4a square. So, 4a square, if you multiply this, so that what you get is this is plus and this is minus. So, it gets cancelled. So, you left with only this one. So, this is the same, okay, and you have dx. So, this is equal to 1 by root 2 pi minus infinity to infinity. So, this is nothing to do with this x variable. So, I can take it out. So, you get e power minus xi square by 4a square minus infinity infinity e power minus a x plus I xi by 2a whole square dx. So, I am doing integration with respect to dx. So, what I do is I try to put this a x plus I xi, this is a complex number, xi is a real number because it is a Fourier thing, xi is positive, okay. Xi is full real line. So, xi is belongs to the real number, and you have this, you call this some t, then what you get is dx you want. So, a dx, this is a constant and this is equal to, so I is a complex number. So, you have dt. So, if you do this, what happens to these limits? Limits becomes t limits at x equal to minus infinity. What happens to t? T is a into x, ax is minus infinity. So, let us assume that a is positive, okay. So, a is positive is it does not matter, because here if a is negative at x equal to minus infinity, it is going to be plus infinity. So, if I choose a is positive, so a into x will be minus infinity plus I xi by 2a, okay, I xi by 2a. So, this whole thing is constant. So, you have this one at x equal to plus infinity, t becomes plus infinity plus this constant, okay. So, try to use that, what you get is e power minus I square by 4a square 1 by divided by root 2 pi times minus, now what you get is minus infinity plus some constant, complex number though, infinity plus, rather you write a constant first, constant plus infinity. So, it does not matter. So, you have a plus infinity plus I times xi divided by 2a. So, this is what you have, and this becomes e power minus t square dt, dt by a is my dx. So, you have 1 by a comes out. This is what is the integral now. This integral if you want to find out, because the integration is over, so this is basically if you look at the complex plane is actually it is it is like a plane r square. You can identify complex plane with r square, okay, r2 is like a usual plane. So what is the main difference in complex plane and real plane? Real plane, so you have minus infinity infinity as your thing, and in the complex plane this you can identify with the c. At every point you can identify with this c. So if you think of a complex plane, what you need is you need an integral from minus infinity to, so let us say if I xi divided by 2a is this one, if y equal to this, and this is the line over which you want the integral, okay. To get this integral, this is your x axis and this is your y axis, okay. And to get this integral, so every point is like x y, which is actually x plus I y, you can identify like that in the plane. So you want integral over this in the complex plane, and so how do I do this? So first of all, for any curve in the complex plane, so let us call this z of t. So this is a curve is any smooth curve, piecewise continuous curve. That means, so I will not just get into the details. What you do is you make any curve which is a parameterization. So z of t is x of t plus I times y of t. T belongs to some a to b. So if you parameterize a curve, so you fix t equal to a, this is this point, this is x of t, x of a and y of a. As you t moves along, move from a to b, you actually move over this line, over this curve is going to be, this is x, this is z at a, z at b, this is z at b and this is z at a. So that is x of x a y a and here z a x a y x b y b. So this is how you parameterize the integral over this curve. Let us call this some gamma. So you want to have a gamma f of z. So gamma is a curve in the plane, in the complex plane. So you have a z belongs to gamma f of z dz. So what is this becomes? So if you do this one, so if you try to do this one, dz is, what is dz? Dz by dt. If you do, that is actually z dash of t into, right, that is basically z dash of t. You can do, because z is a function of t, you can differentiate, right. So that that implies what you can write dz as z dash of t into dt. So I write this dz as z dash of t dt, and t is now varying between a to b, so you can write a to b, and f of z of t, because z is nothing but z of t. So everything in terms of t you want. So this is the integral, this is the real integral which you know, usual integral, usual Riemann integral or whatever usual integration which you do, normal integration over a real variable. So if you have a complex variable like this, complex integration over a curve which is in the complex plane, and z is a complex number, you parameterize such a curve, such a gamma. If you parameterize such gamma, if you can parameterize like this, for example this is your gamma, thus what is its parameterization? X equal to t, y equal to simply constant z by 2a. So t is between minus infinity to infinity. If I choose like this, x plus z of t is x of t, that is t plus I times xi by 2a. So t is, z of t is t plus I xi by 2a, t is between minus infinity infinity, that is actually parameterization for this full line, infinite line, okay. But you know only finite line. So what we do to calculate over a finite line, so to get this infinite line, okay. So because they see if even for real integral, this is the, what is the meaning of this real integral f of t dt? This is actually limit some k goes to infinity, you fix it as minus k to k, f of t dt, okay. This your usual integral. When you finally after calculating, if you allow k goes to infinity, that is improper integral like this. So what you have is an improper integral over a curve, okay. So, how do I calculate? So, how do I put this? So, to calculate over this directly, if you put it, you will not be able to get it. So, you will see even if you put directly, so integral over that, we can do that. So, okay, let us you see that. So, integral over, let us say minus infinity to plus I xi by 2a and plus infinity plus I xi by 2a e power minus t square dt. Okay. So, t is now actually z is because t belongs to this set minus infinity. So, this line you are in the complex plane. So, this is kind of minus z square, z is this one, z is this. So, if you rewrite this t from minus infinity infinity and e power minus what happens to z of t, that is t plus I xi by 2a whole square. Okay. Dz is simply dt because that is a constant. So, you do not really gain anything, you exactly got what you want. So, just by parameterization and evaluating over, you will not be able to get it. Okay. So, this you can get it actually, this is a real function, this is the f of z of t is some function of t plus I times another function of t. So, it is a complex valued function, function over a real variable t. So, such a thing we have, but here you try to write like that, this is actually minus infinity infinity e power minus t square. Now, t is real, minus plus xi square by 4a square into dt, that is your real part, and imaginary part is minus infinity infinity. What you get is no, this is not the real part. What is the real part? This is the real part, and you have e power minus I xi by 2a, that will give you cos xi by 2a. Okay, that is what you get. So, cos xi square, because what you get is e power minus I xi x, right, cos xi x, right, cos psi t. What exactly you get? T square minus t square minus plus xi square by a square. So, 2 times 2 goes t xi by a. So, t xi by a, this is what you get. Okay. So, what is that one? So, your real part if you take cos xi t by a into dt plus integral minus infinity, this is the imaginary part I times same e power minus t square plus xi square by 4a square. Now, you get sin xi t by a into dt. So, these integrals you do not know how to evaluate them. So, these are not known integrals which you can evaluate easily, but there is a complex variable technique in complex variables. In complex variables, what there is something called as a technique called contour integration technique, that is based on a Cauchy theorem. So, I will digress here. So, our aim is to find this integral. So, what you get is we digress a little bit here. So, we write what is called Cauchy's theorem. Cauchy's theorem in complex variable. If f is analytic, what is the mean by analytic? If f is analytic, f of z is an analytic function. That means f of x is f dash of x, all the partial derivatives. Okay, dou f. So, f of z means f of x plus I y. If you substitute, this is actually u of x y plus I times v of x y. This is a complex real part and imaginary part you take, and all these partial derivatives dou u by dou x, dou u by dou y, dou v by dou x, dou v by dou y, all these exist and they are continuous and they satisfy or continuous, and you have a Cauchy-Riemann equations, CR equations, Cauchy-Riemann equations. Those are dou u by dou x equal to dou v by dou y and dou u by dou y equal to minus dou v by dou x. If they satisfy some equations like this and all these partial derivatives are continuous, then you say that this is analytic function. Okay. So, that you, so if you just get into some book on complex numbers, complex variable, complex calculus, complex number calculus, complex functions theory, if you read, you simply calculate what is its derivative of a function. So, that you take in the plane any function, if you want to have a f of z, f derivative of df by dz, complex derivative is usual way definition is you take any delta z, that may be any z function here, f of z minus f of z plus. So, something like that. So, z is this, and you take any all directions, in any direction you take z plus delta z, then you can calculate f at z plus delta z, that is on the here on the circle. This can be any direction, minus f of z, that is at z, that is the center point, divided by z. If this limit exists in all directions, this need not be simply, you need not come there is a delta z. Okay. If all directions, whichever way, if all direction if you can come, if it exists, this limit is same, then you say that if this exists, then you say that it's a differential, derivative exists, and if its derivative exists and it is also so then you say that it is differentiable at a point, at every point inside and its derivative exists. You take every point and you take a small any neighborhood, you take any small neighborhood of z, you take every point inside here. Now z1, at z1 this is true, df by dz exists in the neighborhood of that. Okay. At every point if you have such a thing, at every point inside if it is still differentiable, that means this limit exists at every, so this means the limit exists at z, that means this exists at z equal to z. Okay. So, let us call this z0, then it is z0. So, at z0 this limit exists, then you say that f is differentiable at z0, and once you have this z0 in the, you take any neighborhood, every point z1, if it is differentiable at z1 also, f is differentiable at every point inside this neighborhood of z, inside this disk. That means you take any point z1, still this it exists, df by dz at z equal to z1, if it exists, that limit exists, then it will say that is analytic function. That is equivalent to say that instead of calculating these limits, this is equivalent to say that you write this function as a real part and imaginary part, and then you look at its partial derivatives, real part, imaginary part, because these are function of two variables. If you remember the calculus, multivariable calculus, this is a function of two variables. So, you have you calculate its partial derivatives, and these are the, and if they are all continuous functions and if they satisfy these Sierra equations, they are actually equivalent to their analytic function. So, that is why I said that is how we characterize these analytic functions. So, if such an analytic function if you take, so let me write the Cauchy theorem. Cauchy theorem we will write it here. So, if f is Cauchy theorem, if f is analytic function, f of z is analytic in a open, it is in a region. So, this means region means it is connected every point to every point, you can always connect it by a line inside, but that is inside that region. If it is a open, that means open means you take every point, I can always construct a circle, that is disk entirely in it, that is open. Connected means you take any 2 points, I can always connect it by a line which is entirely in the domain. So, that is such a call is domain. Domain means open set, just like a open interval, you take every point, I can always construct a small interval which is entirely into that. So, like there is open connected set is called domain. So, such a thing, connected means you take any points in that domain, I can always connect with a line entirely into it. Okay. So, such a thing is called analytic in a domain, omega. So, let me call this omega, omega is the domain inside. Okay. Then, and if I call this this boundary of that is dou omega, then integral over f of z over d omega dz is always 0. This is true for every omega inside the domain D. So, let us call this domain D, and then you take this this omega is into some bigger domain. So, this is your D, this is actually your D, and in that you consider this gamma is your omega is your curve, omega is curve, omega for every omega closed curve omega, let me call this closed curve omega which is in D. Okay. No, so every, let me say every for every domain, you consider in D, for every domain in this, for once you have every domain in D closed domain. So, once you have say domain, so instead of putting it this way make you confused. So, what you do is so you have initially one domain D which is a connected open set, okay. This is your D. Now, you consider any closed curve, closed smooth curve, okay. So, if we call this gamma, so let me call this gamma equal to 0 or gamma, for example, gamma closed, this because it is a closed, I give the orientation, it is going from anti-clockwise direction. So, if anti-clockwise is a positive orientation, if you go with the clockwise direction, that is negative orientation. So, whichever is you can think of. So, why I choose this, if you go counterclockwise, why I make it positive orientation, because you when you move on the curve, if you are on the boundary, as you move along the counterclockwise direction, your domain is on your left hand side, that I fix as positive orientation. If you move along the line, so that when you see right side your domain, right side your say this is your domain, and if you walk along this inside your domain, this domain is inside, if you go along this side right side, that is negative orientation, because you are moving along like this, you see that always left side is your domain. So, that is why it is positive orientation. So, this is a closed curve, for every closed curve gamma d f of z dz is actually 0 for every gamma inside D, closed curve gamma for every so moment you write gamma, which is if I put right like this, it is a closed curve, okay, for every gamma inside D. That is the meaning of this Cauchy theorem. If you apply this Cauchy theorem, here, now come back to this. If I apply to the Cauchy theorem to this piece, for example, you take you make a rectangle like this. Now, the rectangle is a closed curve. Now, let me put this as a gamma. This is your gamma. This is how you putting as represent your gamma, over which you try to apply your integral over gamma f of z, you take it as e power minus z square, okay. So, if we choose like this, and what you see is on this, if you parameterize this piece and this piece, see each piece you cannot parameterize, everything you cannot parameterize, because this is a rectangle, these are not, this is only piecewise continuous. If it is not, if it is a continuous curve, but it is not smooth, at this point it is not differentiable. So, you cannot represent this as a single parameterized curve, instead you can represent this piece one representation, one parameterization, this piece another parameterization, this is another parameterization. So, like that you have 4 parameterizations. Once you have a 4 parameterizations, and over this one plus this one plus this one plus this one is equal to 0. So, that means, but you see that over this, if you parameterize these 2 pieces, it will be 0, as if this is your x, as x goes to infinity, eventually you want it over full line, right. So, that way you have to allow this x goes to infinity or a, okay. So, minus a to a, and here a plus this is going to be a comma xi by 2a, and this point is minus a comma xi by 2a. So, eventually when you allow a goes to infinity, so you see that this piece will become minus what you want, this minus infinity plus I xi by 2a to plus infinity I xi by 2a. This piece becomes, as a goes to infinity, this is going to be minus infinity to infinity, okay. And this piece, what happens, what is the parameterization? Parameterization for that piece is actually x equal to a, y is equal to 0 to that y is t is between, so that means a plus I t, t is between 0 to xi by 2a. Okay, this is your curve. So, like this if you do, and finally when you allow a goes to infinity, because of this e power minus z square. So, e power, when you substitute this x, z is this, z of t is this, e power minus z square. So, a square comes out, whatever may be a square, z square. So, you can write a plus e power minus a plus I t whole square. So, what is this one? So, this is e power minus a square into whatever e power minus 2 I a t into e power plus t square, for example. Okay. So, if I choose like this, so what happens? So, as a goes to infinity, this is going to be 0. So, whatever may be the integral, this integral over that small piece, that is this piece, this is a finite piece. So, it does not matter. So, the integral value is finite, and you have e power minus a square, as a goes to infinity, this is going to be 0. So, like that you can show that this over this is 0. If you parameterize the same way, this way, opposite direction, that is also 0. So, maybe we will try to do this in the next video, we will properly calculate and see this one. Okay. So, once you do this one plus this is 0 and this is plus this one plus this equal to 0, that means this is equal to minus of this one, because you go in the opposite direction, that is a minus of that. So, you have from this to this, that is minus infinity to this is same as minus infinity infinity. You simply replace z with e power minus t square. So, if I apply this, we will try to redo this thing. I will try to calculate this as a complex, I will try to apply this Cauchy theorem and try to get this integral in the next video. So, what you see is, I am just right now I will just orally explain you and I will just directly put it. So, e power minus I square by 4 a square by a into this becomes over this integral, this integral is actually this, that is same as this one. So, that is minus infinity infinity e power minus t square dt. Now, t is complex or does not matter, because you are on the real line. So, this is over this, t is always real, here t is complex. So, that is why you see that both these integrals are same. So, what is this integral? This integral, because this is a how do you calculate this one? Now, again if you have to use the complex, you have to use the calculus, So, how do I calculate this integral? Now, your question is, how do you calculate this integral? E power minus t square dt minus infinity infinity. So, to do this, again let me put it. So, minus infinity to infinity e power minus t square dt. So, what I do is I will try to suppose this is your I t is a dummy variable. So, let me call this x minus x square dx, and I also write I as minus infinity infinity e power minus y square dy, both are same. Now, if you multiply I square both sides, I1 and I2 together I square, and what you see is minus infinity infinity e power minus x square dx into minus infinity infinity e power minus y square dy. X and y are separate variables. So, you can write minus infinity as a iterated integral minus infinity infinity e power minus x square plus y square dx dy. This is how you do. Now, if you use this x equal to r cos theta, y equal to r sin theta, then what happens to x square plus y square? This is r square. So, what happens if you do, if full plane you can represent r is between 0 to infinity and theta is between 0 to 2 pi. Okay. If x y between minus infinity infinity, this becomes, the domain becomes this one. So, your integral become now 0 to r 0 to 2 pi e power minus r square dx dy becomes, this is like a change of variable formula, r dr dx. Okay. So, dx dy becomes in calculus this multivariable calculus. So, you have to find the How do you find this? What is r? Dx dy is actually dx dy is equal to some Jacobian, some modulus, the determinant of modulus of the determinant of some matrix times dr d theta. So, that is what is this j? J is you have to do dx by dr. So, dx by dou x by dou r, dou x by dou r, dou x by dou theta, and similarly dou y by dou r, dou y by dou theta. If you do this one, what is this one? Dou x by dou r, you have cos theta, dou x by dou theta is r minus r sin theta. Here dou y by dou r, that is sin theta, this is r cos theta. So, if you, what is this derivative is simply r cos square theta minus plus r sin square theta. So, that is simply r. So, that is how you get, so dx dy as r dr d theta. This is in polar coordinates. Okay. So, r dr d theta, that is it. So, this is from r is from so actually you should write 0 to 2 pi, 0 to infinity, r dr d theta. Dr is inner integral, d theta is this one. So, it is nothing to do with this theta. So, you have 2 pi times, and this e power I r is you can write 1 by 2 e power minus r square, minus of that. If you differentiate this, minus plus, so minus 2r. So, r into e power minus r square. So, for this if you put these limits, so 2 goes pi, so you get simply pi. Okay. You simply have e power minus 0 is 1, so you have pi. So, together you have this pi. So, I square is what you got is I square is pi, that implies I is root pi. So, what is I? I is actually what you want here. So, here this value of this integral is root pi, that root pi goes 1 by root 2 into a e power minus xi square by 4 a square is the result of your Fourier transform of given function. Okay. Now, xi is actually full real line. So, if I choose a equal to 1 by root 2 in your function, what happens to your function? F x is e power minus a square is x square, a square is 1 by 2. So, this is your function. Now, what happens to your Fourier transform is 1 by, is a is 1 by root 2, that goes, and what you simply have e power minus xi square, a square is 1 by 2, so again xi square by 2. So, you see that both functions are same. Fourier transform is Fourier transform of this function is itself as a function of xi. So, that is called self reciprocal with respect to the Fourier transform. This function is self reciprocal. So, basically it reflects, once you it takes the function to the function itself. Okay. Fourier transform takes the function to itself. So, inverse transform also takes from here to here. So, that is the meaning. So, in the next video we will try to calculate again, I will try to rigorously, I will just do the parameterization for this contour. This is called contour because it is closed, piecewise closed curve, that is called contour in complex variables. You take this contour closed one and your function is e power minus z square, that is analytic function, f of z is e power minus z square analytic function inside, okay, inside and on this domain, on this including the boundary, it is the analytic function. And to see that, check the analyticity, you can verify that all these you can verify as a student. So, you can just calculate e power minus z square means e power minus x square plus y square, x square minus y square, right, x square x plus I y whole square, that is x square minus y square plus 2 minus 2 x y I, right. So, such a thing if you take, this is your u. So, u is e power minus x square minus y square this is going to be cos 2xy plus I times e power minus x square minus y square sin 2xy. So, this is your v, this is your u. You calculate all these derivatives, they are continuous as a real valued functions, and you see that these CR equations are satisfied. Cauchy Riemann equations are satisfied. This is Cauchy Riemann equations. They are satisfied by these two, and you can verify that is a analytic function. This is analytic function in the domain, that is that rectangle, and that implies by this theorem, which you can assume that this over that real over that boundary, that means on the rectangle that equation integral value is 0. The only thing is then this plus opposite direction has to be 0, because these parts I will show that is 0, and finally because this on this part is actually minus of this way. So, that means this is same as this way, that is actually what you want is from this point to this point to this point, it should be same as this point to this point. So, that is how I have written minus this to this to is the same as minus infinity infinity. This is over real line, this is over that upper piece of the rectangle. So, this is this one. Okay. So, I will try to show that one in the next video. So, what you have seen today is you calculated e power minus a square x square, which is a rapidly decreasing function, which looks like a bell curve and also called Gaussian kernel in the heat equation. Heat kernel is also called heat kernel, it comes in the applications of partial differential equations. So, there you may, if you want to solve some boundary value problems, you want to apply if you like to solve by Fourier transform, you may have to find the Fourier transform of such rapidly decreasing functions. So, we calculate this rapidly decreasing function. With that technique we end up getting this Fourier this complex integral, which we see that it is a real integral, and this is again from the calculus you can show that its actual value is pi. So, that pi, if you this root pi, so that root pi goes, what you end up is this one. So, once you choose a particular value, it is a self, so this function e power minus x square by 2 goes to the Fourier transform of that goes to the itself. That is the meaning of what we have done. So, in the next video we will try to show again this complex, how this complex integral over that upper part and is same as on the real line. Okay. We will see that in the next video, along with and then we will move on to find the transform find the properties of the Fourier transform, start from the linearity and so on, whatever we have done for the finite signal. Okay. So, you have a periodic signal, over a periodic signal whatever properties that we have done we will try to see here also, and then we will end up finally eventually we will try to find Fourier, we will try to prove rigorously Fourier integral theorem. Okay. We will see all that in the coming videos. Thank you very much.